Comes on everyone, let's start off. Last thing that we did wave speed and then energy in a progressive wave. I hope everyone has gone through that stuff. It was a lot of math and a lot of equations. Great. Next thing. Principle of superposition. So what this thing says, we have used this multiple times before. If you have two waves, are superposed at a point, the resultant would be the vector sum velocity at a point. Vector sum of the individual waves. So what does this mean? So let's say if you have two waves going on a string and one wave is pushing the particle by 3 and the other wave is pushing the particle by 2, and then the resultant would be 3 plus 2. So like I said, remember wave is actually nothing but a disturbance which is propagating in the medium. So what it does, it moves the particles. Now if you're sending two waves and each one moves the particle independently, we can just add them up. So let me show you a case. Let's say waves are along the same plane of oscillation. That means if you have y1 is equal to a sine omega t minus kx and y2 is equal to a sine omega t minus kx plus 5. So if you have two waves like this, both are out of phase by 5. I hope you guys remember how to add two sine functions with a phase angle. Anyone remember? We call it phasors. We have done this again in SHM. Y resultant is y1 plus y2. So how do we add two functions? You should go to SHM. It's a very important thing, and you're going to use it again. This is the whole concept. So whenever you have two vectors like this, a sine omega t and b sine omega t plus phi, you can treat the amplitude as the magnitude of the vector and the phase angle as the angle with the reference line. So a sine omega t, the amplitude is a and the phase angle is 0. B sine omega t plus phi, b is the vector and phi is the angle between them. Page number 41, SHM, I'll write it down. You can refer that. Definitely revise this concept because we are going to use this again in alternating current. So when you add these two vectors, we have a, I can take this as a1 and a2. The other vector will be a2 and the phase angle is phi. The resultant of these two vectors will be some r and this angle will be alpha. R will be root over parallelogram law of vectors a1 square plus a2 square plus 2 a1 a2 cos phi. And the resultant will be tan alpha will be a2 sine phi. This is parallelogram law of vectors. I hope you remember. In case you forgot, you should check out that also. That would be the resultant of these two vectors. So the resultant vector would be r into sine omega t kx omega t minus kx plus alpha. This is a very neat technique, to add two sine functions. We use this in SHM, we use this thing in waves, we also use this thing in alternating current, which comes later on, and also in wave optics. So definitely make sure to go through the phases. Kate. So you can convert a sine function into a vector, and then you can add them and get back the sine function again. So here, if you see, right, both the waves are pushing the particle in y direction. So if wave 1 pushes you by y1 and wave 2 pushes you by y2, then both of them together will push you by y1 plus y2. So this is when they're in the same plane. What happens if they're not in the same plane? Case 2, waves are oscillating in different planes. What do you mean by different planes? Think of it like this. If you have a string, I can make it go up and down, or I can make it go left and right also, isn't it? You can take a string, you can do up and down, or you can do left and right. You can send waves in different planes. So example, when you write the equation y is equal to a sine k x minus omega t, j cap. So what you're saying is this x here is the direction of wave propagation. So the wave is traveling in x-axis. But the particles are oscillating in y-axis. Meaning they would look something of this sort. If you take a photograph of the wave, this is how the wave will look like. This is your x-axis and this was your y-axis. Now, if you take another wave, z is equal to, let's say, b. For simplicity, I'll keep the function same without a phase angle. This would be k cap, meaning here the particles are oscillating in z direction. This can become really complex if you change the amplitude and the phase angles and all. So we'll keep it simple. Wave is still moving in x-axis. So this x inside the function, right, this will tell you which way you're traveling. The outside one will tell you which way the particles are moving. Wave moves along x-axis. That means if I combine this, so this is how the green one look like. See, that is your z-axis. Now, if you combine both of them, so one guy is pushing you in y direction, the other guy is pushing you in z direction, you'll get a wave. This was your y, this was your z. The wave would go somewhat like this. It will be at an angle. Right? And this amplitude would be root over a square plus b square. That means if someone sends a wave up and down and you also send a wave left and right, they combine together and you get a wave at a diagonal. The string will start oscillating at an angle. I'll show you something like that, but is this clear, everyone? So when you add two pulses, they simply add up. Let me take a more simpler example. So that's the main logic of principal of superposition. A wave is simply pushing the particles in a particular direction. But if instead of one wave, if you send two waves, both of them are pushing in some direction. So the resultant will be the vector sum of both the things. If both are pushing in y, add them directly. If one is pushing in y and one is pushing in z, then we have to add it vectorially. All clear with this logic? Clear, everyone? Vanchika? Amrita? Clear? Advait? Clear? Harshita? Let me show you one example and then I'll show you this. So example, let's say we have a square pulse and we have a triangular pulse. Now, these kind of pulses you can't generate on a what do you call that? On a string. These are basically voltage pulses. You might think like, oh, where do I see this? Ever seen in these movies? The hero is in a hospital, he's about to die, like key. You get like this, that ECG or whatever, and then he's gone to key, he's dead. Like those are actually voltage signals. That kind of, uh, yeah. And then the heroine comes and he will survive. So that's a different story though. Some reason it works out. This is a 1 unit per second. This is also 1 unit per second, and this is also 1 unit. This is also 1 unit, and the distance between them is 2 units. So this is the scenario at t is equal to 0. Now see, so these two waves are coming towards each other and they are trying to meet. So at t is equal to 1 second, see how the picture will look like. T is equal to 1 second, the square pulse and the triangle pulse, they will be exactly like this, meaning they're about to meet now. So for simplicity, I will keep one is blue color and one is red color so that you'll understand. At t is equal to 1.25 second, means if you give 1/4 of a second, the left one will travel 25 centimeters, the right will travel 25 centimeters. So the overlapping rate will be 50%. So this is how they will overlap. You're getting it? They will overlap. So when they overlap, right, you have to add them. When you add these two functions, what do you think you'll get? See, try to understand. The blue ka value is 1, 1, 1, 1, 1, 1. So the height is 1. The red ka value is going 0, 1/4, half, 3/4, 1. So it is increasing gradually. So you can simply say the triangle, this part will climb on the square. So the shape will look like this. You get a discontinuity. This is how the pulse will become. Are you able to visualize how it looks? So whichever part got overlapped, that part will add up. So you're adding a blue line to the red line. So the red line will simply climb on top of it. So you're adding one to every point on the left part of a triangle. This thing will go up. Yeah, that looks like a rhinoceros. Not exactly, but kind of. So if you take 1.5, this will be like this, and the triangle will completely get enclosed like this. So now when you draw this thing will completely, you get a house. This is how it will look at 1.25, and the height of this thing will be 2 units. Are you guys able to visualize this, how it looks? And if I try 1.75 and 2 seconds, they will separate out. So I can keep drawing like that. So this is what will happen. So if you send two waves on both the sides, they simply add up. So this is a
mechanical wave machine will be used to generate pulses and waves.
so this machine which you're seeing, right, is called a honeycomb machine. So how they construct it, they take thin rods, right, and they weld them at the center like a seesaw, and the edges of the rods, right, are connected by strings. So when you push one of them, the other guy also starts swinging. So the whole thing will start looking like a wave. It's called a Winnicombe machine.
It's called the Winnicombe wave machine, and it belongs to the Royal Institution in London. The machine consists of horizontal.
So I'll send this, you can check it out.
Started by moving the third channel bar.
Now see how to, no. So that is a machine there. I hope you can see the rods there. So when you pull up and leave it, right, you can see a pulse. See how it travels.
Down. Watch how the pulse travels along the machine. Each bar in turn goes up and down as the energy is passed along.
Can you see that bump, how it is traveling? So that's your wave pulse. Now, if you observe there, every rod is simply going up and down. The rod is not going left and right, but the bump is traveling forward. So every rod is a particle and the bump is going forward. And you can see the bump is going forward.
The pulse is eventually reflected.
When you hit the fixed end, they actually get inverted. You can see the bump went up, it came down, reversed. We'll talk about that next. What if you send two pulses? You're sending from both the sides. See what happens.
We call them positive pulses. Let's see that again, but this time freeze the pulses.
So as these two are traveling, they freeze the motion here. See, did you see what happened here? The pulse is A, left is A, right is A. Together it becomes 2A. The pulses simply add up.
The pulses add together and form one larger pulse for a moment.
What if we send an opposite pulse, one up and one down?
This time, a positive and a negative pulse move towards each other. Did you see how they combined?
Now see in slow motion there.
Again, and this time freeze the motion.
As they meet, right, observe, they cancel out. Did you see how the string became flat? Because the left guy is pushing you up and the right guy is pushing you down. Together, they cancel out. It feels like it is stationary there. But the waves are still present. They're going to come out now. So the two waves will just pass through each other as if nothing happened. Now, next moment they come out.
This time when the pulses meet, they briefly cancel each other out.
They meet and they just come out.
You have just seen how pulses meet, but do they pass through each other or simply bounce back? We can solve this problem by sending a single pulse from one end and two pulses from the other.
Now see what they're doing. They're sending one big pulse from the left and two small pulses from the right. So if they're bouncing off, then the right side you should get two again and the left side should get one again. But if they're passing, they'll just go through. How the shape looks. See. Can you see how that Strinka shape became? When the two pulses met the big one, this is the new shape. So this is what I was saying. When two pulses add up, they simply add the net displacement. If the left guy is pushing you 2 centimeter and the right guy is pushing you 1 centimeter, together they'll push it 3.
Clearly, the pulses pass through each other and carry on as if they'd never met.
You can clearly see that shape. See how that shape is. The big bump met up with that small bumps, and yeah, this is the new shape of the pulse. This is what I was drawing, like the net shape.
Again.
So that's your principle of superposition. I'll put that in the group. You can check it out. It's a old video, but it's pretty detailed and neat. Everyone clear with that? Now I'll give you something similar. Now you guys draw and tell me what is the shape of this. These are some not tough but decent questions. Let's say we have a triangle. We have a triangle. This is 1 unit. 1 unit. 1 unit per second. So someone is sending two triangular pulses. Again, like I said, these are voltage signals. You cannot generate these kind of pulses on a string because if you see, this becomes undefined slope. These are not waves. These are just pulses. And the distance between same data, I just change the shapes. This is the picture at t is equal to 0. Draw the shape of the pulse at 1.25, 1.5, and 1.75. Let's get this. These are some good questions. These are more like puzzles, but think. I'll give a minute and then I'll show you. You get a very famous shape. So 1 second, they will exactly meet. 1.25 second. This is how the picture would look. T is equal to 1.25. The triangles would be half into each other. This is how it would look, half and half. So just look at the values, okay? The blue one ka value here is 0. So at this point, it is 1, 3/4. This is half. This is 1/4. This is 0. So those are blue ka values coming, and then again 0 and 0 and 0. If you look at the red ka values, this is 0. This is 1/4, right? And somewhere here, this is half. Uh, this is 3/4. This is 1. And then again 0, 0, 0, 0. So what you're doing, right? You are adding these values here. So this is 0 and this thing. So when you say you're adding something, you just have to ask yourself this question. Look at this point here. The blue one is pushing you by 1. The red one is pushing you by 0. That means this particle here will be at height 1. Similarly, this guy is at 3/4 and this guy is 0. So you'll be at 3/4. This guy is half and this guy is 0. So this half and 0 will be exactly on top of each other. So 1/4 is the first time they will meet. So this is how the pulse will look like. So this is height 1. The value will decrease, decrease, decrease. And look at here. I think I didn't draw this properly, but this is half. So half plus 0 is half. Now something interesting happens. As the blue function decreases, at the same time, the red function is increasing. Can you see? So whatever is the value of the blue that is decreasing, the red will compensate for it. So half plus 0 is 0. 1/4 plus 1/4 is 1 by half again. So the function in the middle will become a horizontal line. Then again it would increase and again you get a decrease. You get Batman. Did you see Batman? So, so this part, right? This is the points where the overlap, it actually becomes flat. Meaning, it's a simple way to figure it out. Look at this thing. The blue ka equation will be y is equal to minus x plus something. The red equation will be y is equal to x plus something. So when you add them, you get a constant. Is the shape making sense, everyone? The 2 points where they overlap, you get a constant, and the other two functions will look like this. See, told you it's a famous shape. Continue. 1.75 and 1.5. This is 1.25, everyone. Can you draw for 1.5 and 1.75? Get it? I'll give you a minute more. 1.5 is easy. 1.75 will look again a little weird. Let's get them. Let's see, 1.5. The blue one and the red one will exactly overlap. Again, same story. As the blue is decreasing, the red is increasing. They will compensate. What you get will be a square. You get a shape like this. I hope that was clear. 1.75, that would look a little weird. Look at this value here. This value here, if you see, this is a 0. This is 1/4. This is half. This is 3/4. And this is 1. This is 0. Look at blue ka values. This is 1. This is 3/4. This is half. And this is 0. Now, here, when I add the values, 1 plus half, 3/2, 3/4, 3/4, 3/2, 1 plus half, 3/2. That means wherever they're overlapping, you're getting a 3/2 ka value. So this is how the graph would look. So I'll start with the red ones. So red, it will be like this. Now the overlapping has started. You will get a horizontal thing like this. And then you get the blue one like this. This is how the shape will look like. Do you get the shape? So wherever they overlap, you get a height of 3/2. The other two sides, there is only red and there is only blue. So those guys will be slanting. So this is how the shape looks like. Everyone clear with this thing? Like it's more like a puzzle. So when two pulses meet up, so you can get all these weird kind of shapes. So that is what the pulses do. Any doubts on this? Clear? Next thing. Reflection of a wave. So what happens when a wave hits an obstacle? And this is really important. This will form the foundation for entire wave optics, a part of wave optics. So be very clear with this. Not difficult, but listen. We have two cases. Case one, reflection over a fixed end. So if you take a string and tie it to a wall, and if you generate a pulse, so this is an elastic wall. So you don't lose any energy. So this pulse which is coming here, let's say this is Y incident. This would be A incident into sine kx minus omega t. The wave is traveling right side. After hitting the wall, it gets inverted. So think of it like, perfectly elastic collision. So the particle just bounce down. So the particle will start going backward. So the reflected wave, this is the reflected wave, is given by minus A sine. Now remember, this is traveling on the left-hand side. So it will become kx plus omega t. We don't write a minus sign. So we push the minus sign inside and this will become A sine kx plus omega t plus pi. So this will go out of phase by pi. What do you mean by that? Think about it. Crust became trough, isn't it? Crust meaning plus 90, trough meaning 270. What is the difference? 180. So plus A to minus A, the phase angle is 180 degrees. So there, so the incident wave and the reflected wave are out of phase by 180 degrees. So if a crust goes, you'll get a trough. If a trough goes, you'll get a crust. It will get reversed. So the fixed end will simply push you down. Clear with this? Kaivalya, clear? Trishi? Shreyan? The second case is a free end. Free end or a massless ring. So we have a rod here, and you keep a ring here, and we have a string. So this is a massless smooth ring. This can go up and down. There is no mass. So when a wave comes, this thing is not going to fight back. It will just move with the wave. So if you're sending a wave, y incident is equal to a sine omega t minus kx. So as the wave comes here, the bump will go up. It will rise with this thing. And then when the ring again comes down, the bump will again come back this way. So the bump will be still up only. So crust will remain crust only. So y reflected will be a. The wave is going left side, so kx plus omega t. Yeah, that minus will change the middle. So here the incident wave and the reflected wave are in phase. All clear with this? So let me ask you a question on this. Let's say we are sending a pulse like this. This is 1 unit. This is 1 unit. This is 1 unit. This is also traveling with 1 unit per second. And this is a fixed end. This is a hypothetical wave. This is the scenario at t is equal to 0. So the pulse is going, hitting the wall and coming back. Draw the shape of the pulse. At t is equal to 1.25, 1.5, and 1.75 seconds. See, understand one thing. It is not like, the wave will hit and suddenly the whole thing will reverse. As the wave is hitting, a reflected wave is also generated at the same time. You're getting? It is not like a single event. The wave will just go and just come back. There is a delay. As the wave keeps on hitting the wall, the part whichever got hit, that will keep getting inverted. The whole wave will not invert in one go. So give it a try. I'll show you. First, you figure it out a minute. Like, how do you think it'll look like? Let's see. See this thing. At 1.25 seconds, 1/4 of the wave has already hit the wall. So the 1/4 which has hit the wall, that guy will get inverted. So there is actually an inverted wave coming also on the backside. This is how it looks. This is the picture at 1.25. But you won't see this. What you will see is a resultant. So the blue is pushing +1 and this guy is pushing -1. So the resultant wave will look like this. So this will be half and this will be 1/4. So 1/4 of the wave will get cancelled and the remaining half will remain. Is that making sense? So if 1/4 wave hits the wall, only 1/4 will get reflected. The whole wave will not suddenly reverse. At 1.2, 1.5 seconds, half of the wave has hit the wall. So half of the wave will get inverted. So you'll have one more like this. So the resultant will be a flat line. It looks like there is no wave for a moment. At 1.75 seconds, there is only 1/4 of the wave left on the top. 3/4 of the wave has hit the wall. So 3/4 will get inverted. So this is the thing. The whole wave will not get inverted suddenly. So this will look like this. This would be the shape of the string. Are you getting it? So a wave hitting a wall is generating a reflected wave. So both the waves are present at the same time. So there are two waves which are going in opposite direction. At 2 seconds, the whole wave will come out. So unlike a particle, right, which hits a wall and suddenly reverses, this will take time. The wave will hit and then will keep processing it. All clear with this? So a reflected wave and an incident wave, both will overlap. Next thing. So what if it is not a fixed wall? Every time you won't be so lucky to get a fixed wall. So waves on a composite string. This is again another good stuff. This could be an advanced paragraph. So this can be treated as a theory and question. So let's see. Waves on a composite string. Case 1. Let's say you have connected a thin string to a thick string. A thick rope and a thin rope. So let's say this is mu1. Mu1 is your linear density and mu2. So mu2 is greater than mu1. So you're going from rarer to denser. This point is your x is equal to 0. So this is denser, this is rarer. This is your y incident, which is a incident sine kx minus omega t. Now, when this wave hits the point of intersection, it is not exactly a fixed end, but it is heavy. So it will behave like a partially fixed point. So the reflected wave will be inverted, but at the same time, because it's not exactly infinity, it will also move a little. It will act like a partially free end. You also get a transmitted wave. The wave will split into two pieces. And this is called y transmitted. This would be a transmitted sine. Now remember, the wave ka thing has changed, so it will not remain the same thing. It will be k dash. K ka value will change. I'll just take it as omega t minus kx. This will be omega t. Frequency will remain same because frequency does not change when you go from one medium to another medium. This guy will get reflected. This will be y reflected. So whenever you hit another string, you always get a reflected wave and a transmitted wave. So this would be minus AR sine. You're going backward, so plus, and it is the same string. So omega t and kx will remain same. So be careful. K will be different on both the sides. If you change the string, wave speed will change, but frequency doesn't change. So this is one case. Case 2, you're going from a thick string to a thin string. Mu1 is greater than mu2. Now this point will act like a free end. So the reflected wave will be like this guy. It will be still in the same phase. It's like, think of like this. If a cycle goes and hits a lorry, cycle will bounce back. Lorry goes and hits a cycle, it will go with the cycle. So it'll just push forward. It will not get inverted. So this will be your y incident, which is A incident sine omega t minus kx. After hitting this bump, you will get a reflected wave and a transmitted wave. You always get two waves. This will be y reflected, which will be A reflected sine omega t. Frequency will remain same plus kx because it is going backward. This guy will become y transmitted, which will be A transmitted sine omega t minus k dash x. K will not remain same. So few things here. Frequency remains same. Frequency does not change on the medium. If you send it there, it will remain same. And we also know V wave is equal to omega by k. And we also know V wave is equal to root over tension by mu. So since omega will remain same, tension will remain same because it is the same string, we can say k is proportional to root mu. There, this is a relation between them. So k by k dash is given by root over mu1 by mu2. So k ka value will change on both the sides. The wavelength will change. So when a wave goes from one medium to another medium, the wavelength changes. Just to give a crude example, listen to this example. Why wavelength changes? Imagine we have, 5 of your friends, all are walking in a line. Let's say all are going with 1 meter per second, 1 meter per second. And the distance between them is 1 meter, 1 meter, and 1 meter. As you 5 people are walking in a straight line, suddenly imagine you started entering a very crowded area. The whole thing is crowded, market kind of thing. The moment the first person enters the crowd, he will slow down. His speed will become something like 0.8 meter per second. But the guy behind you is still coming with 1 meter per second. By the time this guy enters here, the distance would have decreased to some 0.8 meter or something. Making sense? They start getting closer. So once you enter inside, if you see, the wavelength is becoming smaller. They're getting closer and closer. The moment this guy leaves the crowd, again his speed will become 1 meter per second. But the guy behind is coming with 0.8 meter per second. So the distance will increase again. Distance will again become 1 meter. Did you observe what is happening? So if I try to draw a wave, this is how it looks, everyone. So the waves are coming like this. Once you enter inside, the waves will get compressed. And once you come out, again, waves will expand. They get closer. The wavelength decreases, speed decreases, but frequency remains same. If you send 5 people, there'll be 5 people only. You won't get 10 people out of the crowd. That would be interesting, but it doesn't happen. So number of waves per second is the frequency. So frequency doesn't change when you cross a medium. Wavelength will change and speed will change. All clear with this? But still there is more. How do we find that A reflected and A transmitted? So let's see that thing, how it works. So we will do it in general, but we can use that for anything. So let's say we have a wave. These are two different strings. I'll just make it more dark. This point is your x is equal to 0. So this is y incident is equal to A incident sine k omega t minus kx. Now be careful here. Just listen carefully here. It can be little confusing here. Now when this pulse is hitting that's intersection, remember you suddenly won't reverse. It will take time. As this incident pulse is hitting the intersection, at the same time you get a reflected pulse and a transmitted pulse. So as you're hitting here, you are getting the two pulses are being generated at the same time. So two pulses are being generated. I'm assuming it is up only. The science will take care of it later on. So this was the intersection, x is equal to 0. So this is y transmitted, which will be A transmitted sine omega t plus k dash x. This reflected will be going behind. So y reflected will be a reflected sine omega t plus kx. Now consider 2 points just on the left-hand side and just on the right-hand side. Now tell me one thing. The incident wave is on which string? Left or right string? Incident wave is on the left string. Reflected wave is on which string? The left string. Where is the transmitted wave? On the right strings. That means the reason why A will go is because of two waves, which is the reflected and the incident wave. So the point A is on a mu1 string. So displacement of A, so A and B are 2 points on the string 1 and 2. I'll write here A and B are points on the string 1 and 2, very close to x is equal to 0. Now, most people, what they think? They think, sir, y incident should be equal to y reflected plus y transmitted. Because logic ये होता है, incident wave is becoming reflected plus transmitted. No, that is wrong. That is a wrong way of thinking. You should not think like, the wave will come and split into two parts. You should think like this. If you look at on the left string mu1, there are two waves on the left string. On the right string, there is only one wave. Agreed? So every particle that moves on the left string is because of these two waves. The incident and reflected are combining with each other and they're making the particles move. The particles on the right side are moving only because of the transmitted wave, because initially there is nothing on the right hand side. Are you getting how to interpret that? Left is one different string, right is a different string. Left mein there are two waves, right mein there is only one wave. So anyone who moves on the left hand side, for example, YA, is because of Y incident plus Y reflected. The resultant of these two waves will move the particle A. Similarly, every particle on the right side YB will move because of the transmitted wave. So this is the incident and the reflected will superpose. That is the meaning of it. Don't say one wave will come and split into two. Waves don't split like that. Displacements don't split like that. Incident and reflected superpose. That's your main thing there. So now I will argue, because the string is always connected, YA must be equal to YB. Why? If YA is not equal to YB, the string will break. YA must be equal to YB because since wave is continuous. If you say, suppose if they're different, let's say YA is 5 centimeters and YB is 3 centimeters. You know the meaning of this? Meaning the string will look like this. It will break at x is equal to 0 and the string will generate like this. So it's a discontinuity. You cannot have a string like this. Is that making sense? Think of like this, your right eye and the left eye, right? When you move your head up and down, the right eye and the left eye should have same displacement. If your right eye and the left eye are going different heights, that means your head is gone. Just imagine your left eye is moving 10 centimeters up and right eye is coming 20 centimeters down. Means what happened? Your head is broken into two pieces, isn't it? It has become a horror movie now. So if you want your head to be intact, both the eyes should go together and come down together. Is that making sense? If your left eye and the right eye are going to different displacements, that means your head is going up and down, like maybe an octopus ka head. You're not intact anymore. You become your head will be a discontinuous head. So kind of like that. So since YA must be equal to YB or else the string will break, when we equate them, we get Y incident plus Y reflected must be equal to Y transmitted. This is the most confusing part because most people think incident will become reflected plus transmitted. It happened, but not for this. That is a wrong way of interpreting the displacement. So this you have to be careful. And then at x is equal to 0, because you are checking at x is equal to 0, this will get A incident sine omega t plus A reflected sine omega t. will be A transmitted sine omega t. This is our first equation. A incident plus A reflected becomes A transmitted. A reflected can be plus or minus. Don't worry about that. Because plus and minus indicates plus means it is up and negative means it is down. Then when can you say incident is reflected plus transmitted? You can say that for energy. The total power coming from left hand side will split into two parts because energy is a scalar. You can do that. So the total power that is incident from the left hand side must have gone into the reflected and the transmitted. This argument is right. But for the displacement of a particle, you have to take the two waves. So yeah, because y is the displacement of a particle, y is not a wave. So what is the power curve formula? I hope you remember last class we did of mu1 A incident square omega square V wave. That is V1. This would be reflected is also on the left hand side. Mu1 A reflected square omega square V2. This is half mu2 A transmitted square omega square V2. This is also V1. That's your power guy equation. Total power coming is equal to splitting thing. And we also know V is equal to root over T by mu. Tension will be same because they're connected with a string. So tension is same. Omega is same. Omega will cancel. Half will cancel. Tension will cancel. You end up with root over mu1 A incident square is equal to root over mu1 A reflected square plus root over mu2 A transmitted square. This is your second equation, everyone. Or you can even do something better. I can write mu1 as 1 by V. So A incident square by V1 is equal to A reflected square by V1 plus A transmitted square by V2. Because see, incident and the reflected both are on the same string, so they will have same wave speed. This is your second equation, which comes from energy conservation. Please have a look at these two equations. So this equation comes from the boundary condition. The string has to be intact. So all the points on the left side of the origin and the points on the right side of the origin should go together and come down together, or else the string will break. But the points on the left hand side are moving because of two waves. These two waves are pushing the particles on the left. This wave is pushing the particles on the right. So y incident plus y reflected should balance y transmitted. And since you're taking at origin, when you put x is equal to 0, these terms will go off. I simply end up with AI sine omega t, AR sine omega t, AT sine omega t. Sine omega t cancels off. That's why I ended up with AI plus AR is AT. The second one makes more sense, energy conservation. Whatever energy is coming must split into transmitted and reflected. You can do this for energy. Energy incoming is equal to energy outgoing. But this argument is something else. This is displacements. Now we have two equations and two unknowns. From here, I need to find AR and AT. So let's solve them. Get A transmitted and substitute in this. A incident square by V1 is equal to A reflected square by V1, and A transmitted is A incident plus A reflected square by V2. I replaced A transmitted here. Send it this side, we'll get A incident square minus A reflected square by V1 is equal to A incident plus A reflected whole square by V2. This is looking like A plus B into A minus B. So this will be A incident minus A reflected by V1, and this will be A incident plus A reflected by V2. Cross multiply and expand this up. So you'll get A reflected will be V2 minus V1 by V2 plus V1 into A incident. And similarly, when you solve this, we get A transmitted will be 2 times V2 by, you should remember this, meaning if you can derive, fine, but this itself will be a whole advanced paragraph question. V1 is the speed of the incident wave. So that's how you can remember this. V2 is the speed of reflected wave, transmitted wave. So we define something called coefficient of reflection, which is nothing but A reflection by A incident. This ratio is called coefficient of reflection, which is V2 minus V1 by V2 plus V1. So this tells you how much fraction got reflected. Coefficient of transmission. Which will be A transmitted by A incident, which is 2V2 by V1 plus V2. Quite useful stuff. These itself are proper questions there. So these things are stuff. YA is this thing, Nasina, Vedika. Where is the particle A? A is on the left string. On the left string, which waves are there on the left string? The incident wave is coming, the reflected is going. So there are two waves on the left string. And both the strings are pushing, right? The incident is pushing with AI and this guy is pushing with AR, so resultant. And V wave is equal to omega by K. I did write it before, I will write it down once. So, and omega is constant. So actually, if you can find the wave speed, right, it becomes pretty easy to get everything. So V1, K1 is equal to V2, K2. This is the relation between that K1 and K2. Now, if you can remember, great. If you can't remember, you should know how to derive. So yeah, that you need to figure out like, but if they ask you, this itself is a question directly. Now you know how to find the reflected and the transmitted equations if I give you incident. You can copy it down. You will need this for the next problem. But I would strongly suggest derive this on your own once. This is really a worthy advanced paragraph question. They'll simply define something like this. A reflected by A incident is called coefficient of reflection. Find coefficient of reflection and you're done. And they'll expect you will derive all this stuff. So clear with this? Let's see a question. So we got a thin string and a thick string. So let's say this is mu and this is 4 mu. Y incident is equal to A sine omega t minus kx. Second case, we got a thick string and a thin string. This is 9 mu and this is 4 mu. Two different questions. These are the two cases, right? Thin to heavy, heavy to thin. So we will see both. Find the equation of the transmitted and the reflected wave. That's it. If they ask you for the equation, that is the ultimate thing. Like everything will come. Find equation of the reflected and the transmitted wave. There, if you want, I'll show you the equations again. So how will the equations look like? Look at the equations here. So AT sine omega t plus kx, AR sine omega t, this thing. Wait, I did a mistake here. This is minus everyone. It is still going to the right. That is a minus. Minus, yeah. I wrote it wrong here only. Everywhere else is fine. If you're going to the right, it is minus. If you're going to the left, omega t plus kx. So that is important. think. Take a minute or two. This is how they'll frame a question. I gave you in general. Matlab, you don't worry about plus and minus signs. Everything will take care of it. The A reflected will come plus and minus automatically. Let's see. So what is the formula for so when this guy goes right, I know this will be down and this will be up. We know because you're going from light to heavy. But let's see what the answers will give you. So this is y transmitted and this is y reflected. So first thing, let's find the wave speed. So v is equal to root over t by mu. So proportional to 1 by mu. So v1 by v2 will be 1 by root mu by 1 by root 4 mu. So v1 by v2 is 2:1 ratio. So we just need the ratio there. Okay. Now, what is your A reflected? A reflected will be v2 minus v1 by v2 plus v1 into A incident. V2 is how much? You can substitute the values there. So v1 is 2v2. You will end up with minus A by 3. There you got a negative sign. So y reflected will be minus A by 3. So you take it as plus, the signs will take care of it. Sine, since it is going on the same string, will have same frequency and the same wave speed, but direction is reversed. So plus kx. For A transmitted, it is 2v2 by v1 plus v2 into A. So what is v1? 2v2. So this will be 2A by 3. Now you have to be careful here. V wave is omega by k, and we know omega is equal to v1 k1 is equal to v2 k2. And I know v1 by v2 ka ratio is 2:1. So 2 times k is equal to k dash. That's the relation there. So for this guy will be y transmitted. Amplitude is 2A by 3. Sine, frequency will remain same. So omega, wave is going to the right side, minus sign. K ka value has changed to 2kx. Are you getting how we wrote it? It looks easy because you know the formulas. If you don't know this is a mess actually. You have to derive the whole thing. Are you clear what I did? So you need to get the amplitudes. You need to ask yourself, is it going right or left? Then you need to ask yourself, is K same? Everyone understood this. Now, using the same logic, can you get the second one? I'll give you another minute. That I showed you for the first one, you give a try for the second one. Maybe by 5. Let's see, I don't remember the answer. So this is reflections on a composite string. Here I know I can guess this. Both will be in the same phase. Same story. First, I'll find the wave speed. V1 by V2 will be root over mu2 by mu1. That would be 2:3 ratio. A reflected will be V2 minus V1 by V2 plus V1 into A. So substitute here. How much is this? V1 will be 2V by 3, and this would be 2 by 3, 2 plus 3. I think A by 5, I think. And A transmitted will be 2V2 by V1 plus V2 into A. This will be 2V2 by 2 by 3 plus 1, 6 by 5. And I think you're done there. And V1 K1 is equal to V2 K2. And V1 by V2 is 2 by 3. So this is 2 by 3 K is equal to K dash. So Y reflected will be A by 5. You're going backward. Frequency is same. So omega t plus kx because you're going back. Y transmitted is 6A by 5. Yeah, because you're going from heavy to light, the amplitude became really high. Sine omega is same, but you're going front minus k dash is 2k by 3x. All clear with the steps? Is that making sense, everyone? That's how you do these composite strings. So when a wave hits a string whose density is suddenly changing, it will split into two parts, and this is how you get two waves. Definitely do it on your own again. Once more, the derivation, it's pretty useful. Take a break, come back in 5 minutes, we'll continue from here. Come back by 9:47. Chalo, camps on everyone. There, this is what I was saying. This is the Vinicomb mission. Can you see how it is looking? So there are rods which are hinged at the center, so they can go up and down like a seesaw. On the left side and the right side, now they're tied invisible thread kind of thing. So they're connected. So when you just shake one of them, the other one also moves, and everything will just move one after another. So this is the smaller machine. Rods are small. Then you connect it to a bigger machine, bigger rods. So the smaller rods are like a lighter string. The thicker rods are like a heavier string. So you're connecting a light string to a heavy string. So that point is a coupling point. So there, left right is a small machine, left is a large machine. So light string, heavy string. Now if you send a wave, we should know what will happen. The reflected wave should get inverted, the transmitted wave should go ahead in phase. They kept it in night, they kept some radium. That goes fast, but see it in slow motion. See the wave is coming. Can you see the picture there? What happened? The left wave is up and the right wave is down. It got inverted. I think we can see it in slow motion. See the wave is coming. दिख रहा है wave right side कैसा आ रहा है? The wave is coming from the right side. बीच में there is a blue dot, that is a coupling point. It is hitting it. Now it is hitting that point. Got stuck, I guess. Wait. Can you see how the two waves have got split? You got one transmitted wave in the front and one reflected wave at the back. Let's see that again. Wave is coming. Hits, splits, transmitted wave and a reflected wave. There. So that's how it would look. Get two waves there. Clear with that thing, reflection. The next thing, stationary waves. This is the whole main topic of this entire thing. So, and whatever concepts I'm teaching you here, the exact same thing will work in sound waves. So they actually get covered. So listen to this carefully. First, I will show you this completely with pictures. Then we will do it mathematically, and then we'll try to understand what. So these are called as stationary waves or standing waves. Listen carefully because this is useful. It will also teach you one life skill, which you will see what it is. When two waves of same frequency and amplitude moving in opposite directions are superposed. So they're going opposite to each other. We observe there are certain points which do not move at all. We observe certain points. These are called nodes. They do not move. And certain points move with double the amplitude. This is an observation. These are called antinodes. Great. So what's exactly happening? So see this with pictures. Let's say we have two waves coming from the left and right. So I will take one blue color wave. Right. So this is a blue one. I'm just marking two different colors. And let's say there is a red color wave, which is also coming in. So identical waves, but they're just moving in opposite directions. I think the red is big. Something like this. Now, see, these are two waves coming on a string, okay? Observe this point here at the intersection A. So as these two waves are moving into each other, the blue guy will be something like this. The red guy will be something like this. So this is what will happen to them. Now see what is happening to A. The red one is trying to push the A upward. That's what the red wave will try to do. It is trying to push it upward. At the same time, this blue guy is also trying to push it downward. And if you look at the displacement of A, it will be 0. After some more time, if you give little more time, then what will happen? The blue guy will become something like this. The red guy will become something like this. Now, if you look at this, the red is pushing completely up, plus A. The blue is also pushing minus A. If you look at A will not move again. Matlab, if you look at this point, right, no matter what you do, the two waves are going in such a way, whatever is the red doing, blue is doing in the opposite direction. You're getting it? Because they're in so sync. So if you see here, A never moves. You can wait however long you want. The point A will never move. These two waves will always cancel off. These are called nodes. You're getting what is happening there? Now, similarly, same picture, if you look at little more, I'll draw it like this. I wish I have sine graphs, how to draw them. Then these are the two guys, okay? The red guy is going this way and the blue guy is going this way. We already know this guy is A. So other than A, let's look at one more point. Let's take A and let's also take C. Now remember, even though say the wave is here, the red wave is actually overall it is present. It is not like it is only here. Now see what happens. Next moment when the waves go little forward, the blue wave would look something like this. The red guy will look something, if you push it here, something like this. Now, if you look at A here, it is pushing up. If you look at C here, it is pushing down. If you look at the blue here, it is pushing down. And if you look at blue here, it is pushing up. Meaning A will not move. C also will not move. Can you see this? So there are points, it's not only A, there are multiple points which will not move. Similarly, if I choose one point here, B, if I call this thing as B, or if I call this point as C, all these points will not move. And we can clearly see here, the distance between these 2 points is how much? Lambda by 2. Isn't that half of the wavelength? Is that making sense, everyone? Here, see, I'm not teaching any max or nothing. It is simply superposition. The waves are so symmetrical when they're going through each other, right? They're always canceling out at point A, B, and C. They never meet actually, meaning if you have drawn for C also, it would have been looking something like this. Look at C. The blue is pushing down. The red is pushing up. C cut displacement is also 0. And if you look at this distance, again, this is also lambda by 2. Means for every lambda by 2, you will find a point which won't move. So if you look at here, A, B, C are nodes. So it doesn't happen only at one single point. The whole string may there are multiple points which will not move. And the distance between the consecutive nodes is lambda by 2. Everyone clear with the pictures there? Similarly, if you look at some other point, this guy is A, this guy was B, and this guy was C. Now observe the point here, D. See what is happening. The red one is pushing you down. The blue one is also pushing you down. So here the displacement of D is double actually. It's going double the displacement. Next moment, it would look something like this. This guy will look something like this. If you look at here, the red is pushing with 0. The blue is also pushing 0. Both are 0 basically. So at this point here, displacement is 0. Both are giving you 0. So if you see this point D, right, it is going from 0 to 2A. Sometimes it is going double, sometimes it is not going double. Next moment, if you wait for this, the wave will become like this, and the blue guy also will become like this. They'll again go in sync. So this guy is pushing with A. This guy is also pushing with A. Again, you'll observe the displacement is 2A, this time upward. And you will notice there are points like this. There's a point here E, there's a point here F, and so on. There are multiple points here. So this points D, E, and all these things. So this guy is D, and there is an E here. Even that will do the same thing. Are antinodes. They go from 0 to 2A. They go double the amplitude. They move from minus 2A to 2A. And you can clearly see the distance between them. The distance between B and D is lambda by 4 and lambda by 4. They are exactly in the middle of a nodes. So distance between two consecutive antinodes is lambda by 2. Distance between node and antinode is lambda by 4. There, I didn't write a single equation. We just saw pictures. But are the pictures making sense, everyone? Now, if I combine the whole stuff, it would look something of this sort. So there are points like this. Let's say this guy is A, this guy was B, and this guy was C. This guy was D, and this guy was E, and this guy was F. The length of this thing is lambda by 2. The distance between these two guys was lambda by 4. A, B, C are nodes. So how does this look like actually? Meaning picture wise, so ठीक है, we understood. D, E, F are antinodes. So in every book, right, whenever we write what is a stationary wave, this is how we represent. You draw this 8 shape and we say this is a stationary wave. So what does that actually mean? This understanding is important. What's called a wave driver. It's just a speaker. So look at this, what he has. there is a string tied to a pole on the left. On the left, right, we have a that is called a frequency generator. So by changing the frequency, you can make it go up and down. So that is your source. So the left one, when it goes up and down, it generates a wave. But remember, for stationary wave, you need two waves. Remember, stationary wave, you need two waves, not one.
It's going to pump up and down at whatever frequency, except this guy here. When this guy pumps up and
So when it goes up and down, it goes and hits the fixed end on the right side. Now, what happens when a wave hits the fixed end? You get a reflected wave. So now we are getting an incident wave and a reflected wave. When these both the waves, that is how you create two waves. You don't use two sources. We use one single source. So when this guy goes and hits the reflected wave, you're getting a reflected wave and the incident wave is still being generated. When these two waves will overlap, you will see a pattern of what we talked about.
if I set it to just any old frequency,
Now, if you put any random frequency, it doesn't work. We will see that.
I can, they're not instructive. I set it.
Now, see, if you put a proper frequency, you'll see something. See, there. Can you see how it looks?
Called a standing wave. That is the wave that's down.
Can you see that shape, how it looks like? It looks like a loop. When I was in 11th and 12th, I used to think like, why did this, the string broke into two pieces? It is actually one string. It is going so fast, it gives you an illusion it is a loop. So,
And reflects constructively inter.
can you see the node in the middle? That's not moving at all. Look at the point in the middle.
The next wave comes down right at this point. Now the waves that we here, and that's all they
There.
go.
See the point he's catching? Even after catching, see the wave is still there because that point never moves. So even if you catch it, nothing happens. That's your node basically. That is the point we are talking about. That point never moves in this scenario.
And it still is working. So the node is not moving. Here it's moving.
And can you see the one in the middle? That's going pretty big. That's your anti-node. It's going to -2a to +2a.
Here it's moving up and down. And we'll
Now actually see that in slow motion, you'll understand actually what is happening. There. In slow motion, actually it is looking like this. Can you see the left is going up, right is coming down, right is going up, left is coming down. There is only one string there. It is going so fast, it gives you a feeling it is a loop. That's why it is called a stationary wave or standing wave. It looks stationary, but this is how the particles are moving.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice
Now, if you change the frequency, you can get even more loops.
Well, what's the first one? The first one will be half.
Now, listen to the logic here. Just now we proved, right? Distance between two nodes is lambda by 2. Agreed? So if I increase the frequency, lambda will decrease. If lambda decreases, lambda by 2 will decrease. That means the length of each loop will become smaller. That means we get more loops. So if I increase the frequency, I should get more loops on the string.
8.5.
He is decreasing the frequency. So there we got one big loop now.
And there we go.
See how the string is actually going? The middle one is an antinode now. This is how the string is actually going. But when it goes so fast, it looks like there is a big loop.
Basically, the
How is the picture? See how it is looking? It looks like a loop. But in reality, it is only one string.
scenario of a jump.
If you increase the frequency, you can get two loops. You get increase the frequency more. There, can you see 3 loops?
And there we go. So that's the third harmonic. How many wavelengths? Well, it's 1.5. 1.5.
That's the 1.5 wavelength. So each one is lambda by 2.
And it's easier to see.
If you see in slow motion, you'll see something interesting. See how it goes.
Verify for yourself that it's 1.5 wavelengths.
This is how it is going. Look at this, what is happening. When the left one is going down, the middle one is going up, and the right one is coming down. The left and the right one will go in the same way. They go together up, they come down together. The left and the middle one, they're always out of phase. They're always going up and down in the opposite directions. So the odd numbers will go together. Even numbers will go together. Odd and even will be out of phase. And this is how 3 loops look like in slow motion.
So
If you increase the frequency further, you can get even more loops. This is 6 loops, everyone.
Six harmonic.
There. Can you see the 6 loops? This is what I'm saying. This is how the pattern forms on a string. And look at the whole pattern. It looks like as if there is a loop there. So it looks stationary, or it looks like a wave is standing there. So we call it a stationary wave or a standing wave. So that's the thing. Now it's kind of making little sense. There are some points which do not move. There are some points which move a lot. Make sense? Because see, writing on a paper is something, and after seeing it, it makes like, okay, true. What sir is saying is not bluffing. He's actually saying something right. And that's important. Because waves, mein, that's what I observed. The chapter, right? People get confused because you're just writing equations and doing everything. It all looks vague. But when you actually see, right, everything that we are doing, it feels like, ye to sach hai, ho raha hai. So that belief is more important for this chapter. Now, how do we represent the stationary wave? So we represent it with this loop. So in every book, everywhere, they will show like this. We need to understand what is the meaning of this. We represent stationary waves with this symbol, this infinity kind of looking thing. So what is this exactly? These are actually different positions of the string. These are different positions of the string at different times. Meaning if I draw now, see this is how it looks. So the string is like this. This is the time t1, time t1. Next moment, the string will come little down. This is time t2, time t2. Next moment, the string will become flat. This is time t3 and time t3. The next moment, string will go little down. This is time t4 and time t4. Next moment, the string will go to the other extreme. This is time t5 and time t5. You're getting different times. The string is at different positions. If this happens really fast, you think it is a loop. Is this making sense, everyone? Right? Meaning if I actually continued one more loop here, you will notice something here. So all particles, so there are a few points here. All particles in a loop are in phase, meaning they go to maximum and they come to minimum at the same time. In a loop are in phase. So in phase meaning that is they move, they go to maximum and minimum together. See, your maximum value and my maximum value need not be same, but you go to your maximum, I'll go to my maximum at the same time. They are called in phase. Particles in the consecutive loops are out of phase. Particles in alternate loops or consecutive loops, that is 1, 2, 2, 3, these are out of phase. So 1 is going up, 2 is coming down. Particles in alternate loops are in phase, meaning 1, 3, 5 are in phase. These are some good theoretical questions. That's a little about phase. So how do we write the equation of a stationary wave? Now let's do it mathematically. Remember what did we say? Two waves of same amplitude and same frequency, but coming in the opposite direction. So y1 is equal to a sine kx minus omega t. Y2 is equal to same amplitude, same frequency, but opposite direction. So kx plus omega t. When you add these two, y resultant. Remember principle of superposition. You can just directly add them, y1 plus y2. But you can't add the functions directly. It is looking like sine a plus sine b. And this comes out to be 2a sine kx cos omega t. Sine a plus b cos a minus b by 2. This is your y resultant. Now, this is a very interesting equation. If you look at this equation here, it has two terms here. This cos omega t is looking like SHM. This represents SHM of a particle. So a stationary wave is a combination of two progressive waves. So this represents SHM of a particle at x. What is this term is representing? This is representing amplitude. But look at that, there's something interesting there. This is the amplitude of a particle at a distance x, meaning every particle has different amplitudes. Or at coordinate x. So basically in a stationary wave, all the particles don't have same amplitude. Kind of makes sense. Because see, when I showed you that loop, remember the length of a loop is lambda by 2. So if this is x is equal to 0, this is x is equal to lambda by 2. This is one loop. And look at all the points. Are they at the same height? They're not at the same height. This guy ka height is 2a sine kx. So different particles are at different heights. The guy in the middle, this will go 2a. This is your antinode. This distance would be lambda by 4. So every particle will have different amplitude. So in a stationary wave, all the particles need not have same amplitude. So this particle will never cross this line, this particle will never cross this height, this particle will never cross this height, and so on. All particles are going different heights, and these edges are nodes which will never move. They have zero displacement. The guy in the middle is antinode, that guy will go maximum. I'll call it AN. That's 2A. So different particles have different amplitudes. We are proving this mathematically, but before this I showed you with pictures. Now I'm showing the same thing with max. So I'm not doing two different things. The first was more of an imagination, second thing is more of max. But if I do this first, mathematically you'll understand, but you'll feel like, okay, what? But I hope now you're able to connect both of them. The pictures which I showed you, the video I showed you, and the max functions I'm writing. Connect all of them. They're all talking about the same thing. I'm just trying to approach the problem in three different directions for you. The video will give an imagination. The pictures I showed you, how they're going, they will tell you, okay, they're superposing. This is a mathematical proof. So I'm not talking about three different things. All three are same. So far clear with this? This is your equation. Great. Now the amplitude. So this is the best part. So in a progressive wave, the amplitude was constant. Everyone has different amplitude. Was 2a sine kx. So if you want a node, what is the definition of a node? They will never move. So for a node, amplitude is 0. That means 2a sine kx is 0. That means kx must be equal to n pi. And k is nothing but 2 pi by lambda. Pi will cancel, we get x is equal to n lambda by 2. Means if I put n is equal to 0, 1, 2, I'll get x is equal to 0, lambda by 2, lambda, 3 lambda by 2, and so on. These are all the position of the nodes. There, I proved this mathematically, but we did this before with a picture, isn't it? The same thing I proved here before with a picture. All particles at lambda by 2 will not move. The same thing now I'm proving with an equation. So these are nodes. For antinodes, the amplitude is maximum 2A. So we get sine kx is equal to 1. Kx must be equal to n pi plus minus 1 whole power n pi by 2. Now you can simply write like this thing, x is equal to 2n plus 1 lambda by 4. When you get the values here, we get x is equal to lambda by 4, 3 lambda by 4. There again, you can clearly see these are in the middle. These are antinodes. This is a mathematical proof that the nodes exist and the distance between them is lambda by 2 and all that stuff. All clear with the story. This is the theory of stationary waves. So how do you generate stationary waves? So we have an equipment. It's called sonometer. So this is also an experiment, and it is also the whole set is this. So sonometer. So remember the word. The word is important. This is how it would look. This is how the experimental setup will be. If you go to a lab, you will see something like this. So let me explain you what is the setup. So here we have a mass. This is an adjustable mass. You can change the tension by adding more weight or decreasing the weight. You can change the tension in the string. So this will be tension and this will be mg. You can change the tension. Why you want to change the tension? Because I can change the wave speed. So v wave will be root over t by mu. So by changing tension, I can change the speed on the string. These things are the wedges. These are movable wedges. By moving the wedges, I can change the length of the string. Now, for simplicity, I will just draw the picture like this. The right side is fixed. The left side, we have a block M. This is how I will show henceforth. This is x is equal to 0. This is x is equal to L. And we use a tuning fork F to vibrate the string. Clear with this? Now, I want to generate standing waves or stationary waves on this string. Now, understand the situation. When you created the system, you already had a problem. The left side and the right side are already fixed. Because you're tied to a wall and to a pulley, the strings cannot move. So the first possibility, listen, this is the only condition that you need to satisfy. Do whatever you want, but make sure x is equal to 0 and x is equal to L must be a node. Why must they be a node? Because you're tying it to a wall. You cannot break away from the wall and move. This point also has to be a node, or else the block will oscillate up and down. So this is the only condition you need to satisfy. X is equal to 0 and x is equal to L must be nodes because they're fixed. Okay, that is the only condition. And why is this condition coming? It is coming because of the physical system. Because you're tying it, you have made it a node. Now you tell me, if these two are nodes, what is the first possibility you can get? One single loop, isn't it? This is your first possibility. This point is not moving, satisfied. This point is not moving, satisfied. So the first possibility is you can get one single loop. Lambda by 2 is the distance between them. So lambda by 2 is equal to L. So from here I got wavelength is equal to 2L. Then I know frequency is equal to V by lambda, which is V by 2L. That means if you generate a frequency V by 2L, you get one loop. So we'll call it F1. This is also called as fundamental frequency. So if you want one loop on this string, you should generate this frequency. So you cannot generate whatever frequency you want, because for different frequencies, we get different wavelengths. For example, dekho, If your frequency is very high, you will get a loop like this. But this is not a node, so not satisfied. If you have very high, very low frequency, this is how the loop will be. But this should be a node, not satisfied. You're getting it? Only certain values will satisfy the condition that 0 and L are a node. This is also called as fundamental frequency. So it is the minimum frequency which gives a stationary wave. So that pattern or that loop ka thing which you are saying will not occur for any frequency. This is also called as first harmonic. This is your first possibility. What is the second possibility? Again, remember, you only have to satisfy the condition x is equal to 0 and x is equal to L is a node. So the second condition, I can have two loops. X is equal to L is a node, x is equal to 0 is a node. X is equal to L by 2 is also a node. I don't care about that. You can have any nodes you want in the middle. You just need to satisfy 0 and L is a node. Now what happened? The distance became, this is lambda by 2. The length of one loop is lambda by 2. So we get 2 times lambda by 2 is equal to L. So we get frequency F2 is equal to V by L, V by lambda, which is V by L. This can be written as 2 times V by 2L. So this guy becomes F2 becomes 2 times F1. Means if you want two loops, you have to give double the frequency. So we define something called harmonics. Now, just listen carefully. All these things will suddenly fall in place. You know what is this? You have seen these things. You have used these things. You just don't realize it yet. Harmonics are nothing but integral multiples of fundamental frequency. What is the fundamental frequency? The minimum frequency. So the multiple numbers of that are called harmonics. We also define something called overtones. So these are more technical terms. What is an overtone? These are the frequencies after the fundamental. Whatever frequency you hear after the fundamental are called overtones. You will see the use of this later on. That means the second possibility is a second harmonic because it is at 2 times the minimum frequency. And it is also the first overtone. It is the first frequency after the fundamental over the tone. What is the third possibility? Let me show you one more. I think by now you'll get a sequence. The third possibility, 3 loops. The only condition I need to satisfy, x is equal to 0, x is equal to L is a node. I don't care about anything else in the middle. So again, same story here. So 3 times lambda by 2 is equal to L. We get lambda is equal to 2L by 3. So we get the frequency F3 is equal to V by lambda, which is 3 times V by 2L. You can clearly see F3 is 3 times F1. So if you give multiples of the fundamental frequency, you get multiple loops. So this will be your third harmonic. This is the third, 3 times the fundamental frequency. Second overtone, this is the second frequency after the fundamental. I hope everyone is getting what is an overtone and what is a harmonic. By now, if you see, we got a sequence completely. So I keep on doing this for n loops and you will notice Fn is equal to n into V by 2L. V can be written as n by 2L into root over T by mu. That is your wave speed. There, everyone. This is the formula. What is this formula giving you? This formula is telling you if you want n loops, then generate this much frequency. You want 2 loops, then n is 2. 3 loops is this thing. So Fn is the frequency for the nth harmonic, or n loops. V is the wave speed. T is the tension. L is the length of the string. Mu is the linear density. N is the harmonics, or the number of loops. Now listen to this thing. So if I generate Fn, I get n loops, but I can do the reverse. If I generate n loops, I get frequency back. Does that make sense? If I can generate n loops, I get Fn frequency. So where you have seen this before, you know, a guitar. A guitar is a sonometer. Every musical instrument, every stringed musical instrument is a sonometer. Every musical instrument is based on stationary waves. Now look at this. So next time when you're planning to learn music, this will help theoretically. Now in a guitar, if you observe, guitar or violin, you take any stringed instrument, it's a sonometer. All these work based on what we did right now, stationary waves. Any stringed instrument is a sonometer. Now look at the formula. Fn is equal to n by 2l root t by mu. Okay. Let's see how each thing will move. Did you ever hear this word? I'm tuning the guitar. I'm tuning the instrument. So these screws which are there, if you tighten the screws, you're changing the tension. So if you tighten the screw, you get more tension. If you change the tension, you can change the frequency. So tightening the screw changes the tension. So when the guitar goes offset, right, this is what people are actually doing. You know, they're plucking the string here. Let's say it's supposed to come there as sa. So when you hit here, you should get a sa, 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 but you're not getting sa, you're getting some weird sound. Then you try to tighten the string and you keep waiting, you know, when will you hear that particular sound? So that's what we call as tuning the guitar. So tightening the screw changes tension. And if you look at the strings here, can you see there's a thick string, thin string, much thinner string? You are changing the value of mu. Different thicknesses have different values of mu. So if you hit the same spot for a different string, you don't get same frequency because mu is different. So you can generate 6 different frequencies at the same spots, meaning in this entire line, you get 6 different frequencies. So different thickness have different mu. So that is how you adjust mu ka value in the function. So next time when you go to learn an instrument, right, you will understand why the instructor is telling you hit it here, touch it here and all. So this is your thickness. By changing the thickness, you can change the mu. Second thing, when you put your fingers and you change your positions, you're changing the length of the string. If you put your finger here, then this is the length. If you put your finger here, then this is the length. You're adjusting the length of the string. By placing fingers, you're adjusting the length of the string or whatever you keep there. By placing hand at different positions, you're controlling the length of the string. So you get different frequencies again. All this is to generate frequencies. What is n then? N is another interesting thing. These are called as octaves. If anyone has learned music, you will know this. Sa, re, ga, ma, pa, da, ni. If you continue, you'll get one more sa again. Sa, re, ga, ma, pa, da, ni, sa. You say again a sa in the end. So what is this sa actually? This is your first harmonic sa. I don't remember the frequency exactly, but I think it is around 100 hertz. Meaning, if you generate a frequency of 100 hertz, you'll get sa, 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 sa types. But if you hit 200 hertz, you'll again get a sa, but it'll be a sharper sa. It'll be more sharp. You can hear it as a sa, but it'll be more sharp. So the second sa is a second harmonic sa. So that is the value of n. The harmonics you're changing. And this value must be a multiple of the fundamental frequency. This will be 200 hertz. If you continue to increase the frequency, again you will get a sa. This is the third harmonic sa at 300 hertz. This will be even more sharp. So this is how you actually control a guitar. You can change the value of n, you can change the length, you can change the tension, you can change the mu. By adjusting these 4 values, you can generate whatever frequency you want. The next time you see a guitar, you know what you're looking at. That's your sonometer. So when you're plucking the strings, you're generating the loops, and from there you're getting the frequency. And that's where you get the music from. The next time when you're learning how to play, you know why you have to keep a finger at a certain place, or why you have to tighten the screw, or whatever. Is this making sense, everyone? Is everything now you're able to understand? So this you must have seen multiple times. Any doubts on this? So long back, I was learning violin. It's one of the checklists that I have to learn violin. I learned till Twinkle Twinkle Little Star. After that, I got busy and left it. So being a physics teacher, right? When I'm learning violin, instead of learning violin, I'm doing all this nonsense. Why am I putting my finger here? What is this instrument? Why it is thick? I was thinking and I figured all this stuff like, oh yeah, this guitar is nothing but a sonometer. So the teacher used to tell me, Arun, you have to practice every day at least for 15 minutes. I said, okay. So I used to close all the doors, right? And I used to be in a room alone and I used to practice and I used to feel like the violin is crying. It's like, Arun, leave me, yaar. Don't torture me types. It seriously used to feel like it is crying. Yeah? Then next day I went with the guitar to the teacher and told him violin and told the teacher, like, sir, I think there is something wrong with the violin. It is not tuned. That's what we do now. When you don't understand the question, we say we don't know the concept. The question is wrong. The book is wrong. Theory is wrong. He said, okay, let me have a look at it. He took that violin. He didn't do anything. He played it. Trust me, it was so beautiful. I really felt like, the violin was playing with joy. Then I understood. I am the culprit. I am the nonsense guy. It is not the violin. So, yeah. For the first time in my life, I understood violin can cry. So, anyway, that is my short-lived music career till Twinkle Twinkle Little Star. And then that is the thing that I learned. I'll try some more time in the future again. But that's a bit about stationary waves. So please make sure to go through this. Next class is important. We will do all problems. The theory part is done for stationary waves. We have some really good problems. We will see some basic ones. We will do some different wave equations and stuff. I think we should finish off waves on a string in another 1.5 class. I think, yeah. Okay, I think with that, we'll wrap up for that day. There's a test online on Friday tomorrow. So make sure to give. We have done almost 14-15 questions and a lot of theory today. So make sure to go through this once. I'll see you guys again next Tuesday, same time. So any doubts, anything else, please stay back or else you're free to leave.